Okay, so welcome to the last talk of this session. Our next speaker is Denis Nesterov from ETH Zurich, and is going to talk about spaces of maps between curves for the next hour. Please welcome.
Thank you very much for the introduction, and it's an enormous pleasure to participate in an event like this. And so, the title of my talk is Spaces of Maps Between Curves, and I'll talk about spaces of maps between curves, like stable maps or admissible covers, moduli space of stable maps and moduli space of admissible covers, and then the associated map counting invariants like Hurwitz numbers and Gromov-Witten invariants and the correspondences between them. And so the talk will proceed in a completely historical order. So I'll firstly talk about so-called Hurwitz numbers. So they were defined by Hurwitz in 1902 and can be viewed as the first example of map counting invariants. And then I'll talk about so-called admissible covers, so moduli spaces of admissible covers. They were defined by Harris and Mumford in 1982. Then we'll move on to the so-called stable maps. So they were introduced in the study of topological string theory by Kontsevich. Stable maps in 1995. And then finally, I will talk about the correspondences between those spaces and the associated invariants. So the first correspondence of such kind, which had a profound impact on the study of moduli space of curves and Gromov-Witten invariants, is so-called LSV formula. And it was, so stable maps, it was proven in 95. And finally, it will be the Gromov-Witten Hurwitz correspondence discovered by Okounkov and Pandarin-Panda that is a part of the motivation to study these moduli spaces of maps between curves. And finally, I will state the result that generalizes both of those correspondences. And this is the main theorem of our work with Max Schmidt and Johannes Schmidt. So today. So let us proceed to definition of Hurwitz numbers. So Hurwitz numbers. Hurwitz numbers are something very elegantly simple. So we take partitions of fixed integers d. Let me remind you that partitions are just a bunch of integers whose sum is equal to the integer d. And then to k partitions, we can associate a so-called Hurwitz number. And what is this? This is just a number of ramified covers of a projective plane with ramification specified by these partitions over some fixed points pi. So let me just draw this. You have so what we count genus G. So we count covers of a projective plane where we fix k points such that over those points we have a specified ramification provided by these partitions eta i's. What it means is that over in the preimage of those points, the map is given by z goes to z to the power given by the part of those partitions. And so Hurwitz provided an answer to this question, to the question of how many covers there are with a given ramification profile. And the answer is very simple. So Hurwitz, this can be expressed completely in terms of the representation theory of symmetric groups. So Hurwitz provide an answer in terms of representation theory, so in terms of the symmetric group, and the answer takes the following form. We just count elements of the symmetric group such that they satisfy the relation given by the fundamental group of the punctured projective plane. So this just means that the product of those elements is equal to 1. And then the type, well, when you decompose this, when you provide the cycle decomposition of those elements, then it's governed by these partitions of D. Meaning that if you decompose, well, if you write it as a disjoint cycles, then the length of those disjoint cycles is given by the parts of the partition. So that's the answer of Hurwitz to the question how many ramified covers of P1 with a given ramification profile is. And in fact, these numbers have a beautiful representation theory associated to them. And for example, you can express through this presentation, you can express them in terms of the characters of symmetric groups. And by doing so, for example, you can uncover the fact that those Hurwitz numbers satisfy, well, provide the tau functions for integrable hierarchies like Toda hierarchy. And this is, in fact, in the heart of many results of such kind in inverted geometry, like the Kontsevich-Witten theorem, and so on. So. But of course, you also, instead of taking in projective plane, we can generalize this question of how many covers there are of a given ramification profile to an arbitrary surface, Riemann surface X. So that's what the Hurwitz numbers are. And instead of studying just the numbers associated to covers, we can also study moduli spaces associated to covers. And that leads us to the notion of admissible covers. So what are admissible covers? Well, firstly, we can just consider the moduli space of covers associated to some Riemann surface, projective Riemann surface X with a given ramification profile. So So what is the difference between this setup and this one? Well, here we just postulate that we count ramified covers with fixed branching points. So here points are fixed. But here we allow them to move around. So and that gives rise to not just a finite bunch of points, but to a moduli space of ramified covers. And of course, we can recover the Hurwitz numbers just from considering the naturally associated map from this space of covers to the configuration space of points on X. And then the degree of this map will be exactly equal to the Hurwitz number associated to X with a given ramification profile. The problem with this space is that it's not compact in general, because you can consider two branching points colliding in a limit and giving rise to singularities that are not present in any form in this moduli space, in the way at least we defined it. So, and Harris and Mumford provided a solution to this problem, so to the problem of compactness of these moduli spaces, and this is exactly the notion of admissible covers. Harris. And so how do we compactify it? Well, in order to compactify moduli space, we have to introduce something more degenerate than the specified objects. And in particular, in this case, we can compactify it by allowing the source curves to become nodal, as well as the target curve to acquire P1 bubbles. So let me firstly write it, and then I will also draw pictures to explain what I mean by that. So firstly, this moduli space is just a moduli space from nodal curves to X tilde with exactly the same condition as ramification profile is provided by these partitions eta I, and then there are some other technical conditions that I'll not write down. It would not be necessary for our purposes. And so how does the picture look like? Previously, we had just some nice ramified covers from Riemann surfaces to a fixed target X. Here we have to allow our Riemann surfaces to acquire nodes as well as the target also should acquire P1 bubbles, such that each of the components in the source curve map nicely as a ramified cover on the components in our target curve. So, and such that the ramification profiles are exactly provided by the same partitions of integer d. So here you have some points that move around, and the ramification profile is given by eta I. So this is the moduli space of admissible covers. And it solves the problem of the non-compactness of these spaces of covers with a specified ramification profile. So in fact, even more, these moduli spaces are smooth and irreducible, so it's a compactification in as good as it gets. So why Harris and Mumford introduced those spaces? Those spaces were introduced in the study of the geometry of moduli space of stable curves, and in fact, they used them to show that the moduli space of curves for high enough genus are of general type, so they have a maximum Kodaira dimension. In particular, this moduli space is extremely important for the study of a classical geometry of moduli space of stable curves. And for example, let me just write it. Study of M gene bar. In particular, for example, if you consider moduli space of admissible covers for partitions 2, 2, 2, 2, that will just provide a hyperelliptic locus in the moduli space of stable curves. So those moduli space of admissible covers give rise to a very geometric loci inside moduli space of stable curves. So this is the story of Hurwitz numbers and admissible covers. Let me now talk about stable maps. So stable maps provide another family of moduli spaces of maps associated between curves, and they were introduced by based on the works of Gromov and Witten and other physicists that were introduced by Kontsevich in the algebra geometric setup in '95. And so, what are those moduli spaces of stable maps? So instead of considering covers with the specified ramifications, we can also consider just arbitrary maps between Riemann surfaces without any restriction on what singularity they might have. So this is the notion of admissible, of the stable map. Stable map is just some map from a curve to our fixed target x, such that in fact we don't impose any condition apart from the condition that says that the automorphisms of this map have to be finite. And in particular, so how does it look like? So here we have our target x, and now the source might also be nodal, but there is no restriction on any ramification. So no restriction at all on the ramification, and also on the apart from ramifications, the stable maps might have contracted components. So you might have the whole component that's contracted just to a point in our target x. So this is a depiction of a possible stable map. And just like in the case of covers and Hurwitz numbers, one can associate some kind of a invariant that aims to count maps between Riemann surfaces using the notion of a stable map now. So there we counted admissible covers or covers between our Riemann surfaces. Here we can count now stable maps without any specified ramification profile. And what are those invariants? Well, those are just so-called Gromov-Witten invariants. How we define them? So this involves some extra structure that wasn't necessary in case of the Hurwitz numbers. And the first such structure is provided by evaluation maps. So evaluation maps are given by, well, I haven't been precise enough. Here we also have mark points in our source curves, and the evaluation maps are provided by associating to a map its image with respect to this mark point. But more importantly, we also have so-called psi classes. So psi classes are the first chain classes of line bundles, which are given by the tangent, cotangent spaces at the mark points of the curves. So then Gromov-Witten invariance. Let me write it somewhere else now. So then Gromov-Witten invariants are these integrals on the moduli space of stable maps. Such that we integrate, so we pull back some classes from the cohomology of our target curve X with its evaluation maps. And then we also insert this powers of psi classes and then integrate over this moduli space of stable maps. With a small caveat that the integration has to be defined to serve the needs, and the correct definition is provided by the theory of virtual fundamental classes. So these Gromov-Witten invariants, that are just another way to count maps. And a natural question is how Hurwitz numbers, so the counts of admissible covers with the specified ramification, are related to this more intricate Gromov-Witten kind of invariants, which are defined by the intersection theory on the moduli spaces of stable maps to a fixed target X. And in fact, yeah, so the Hurwitz numbers and Gromov-Witten invariants are related in some deep ways. Let me write this as a slogan. So Hurwitz. Gromov-Witten invariants are related. This leads us to the first kind of the relation that was discovered, which is the so-called LSV formula. Let me now explain what LSV formula is. So this will be the answer to the question, how are they related? The first answer is a LSV formula. And this is discovered by, well, LSV, just abbreviation of the Ekdal, Landau, Shapiro, and Weinstein, who discovered this formula. What this formula states is that if we consider the Hurwitz numbers of a projective line, so Hurwitz numbers associated to some partition eta, and then the rest of the partitions are simple ones, so simple ramifications, then this number is equal to some combinatorial constant times an integral that takes place on a moduli space of stable curves of genus that is determined by the Riemann-Hurwitz formula associated to these partitions, and with the markings given by the number of parts in the partition eta, and the integrand of on the right-hand side is the following classes. So in the numerator, we have the sum of so-called lambda classes, which I will define in a second. And then in the denominator, we have a product of classes given by psi classes. And with the associated to the markings that are provided by the parts of the partition, and such that we have parts of this partition also in front of these psi classes. So let me now specify what all of this means. Firstly, here the star just some combinatorial constant that depends on the number of simple ramifications over here, and also on a partition eta, depending on m and eta. And more importantly, these lambda classes are just the first, the Chern classes of the so-called Hodge bundle, where such that the Hodge bundle is defined by taking the differential forms on our moduli space. So differential forms of curves on the moduli space of stable curves. So this is the LS3 formula. In the way I expressed it, it seems like it doesn't really compare Hurwitz numbers with the Grom-Witten invariants, but with something else. But in fact, this integrand on the right-hand side essentially is a Grom-Witten invariant associated to P1. So if you localize on the moduli space of stable curves to P1, you get this as a localization contribution. Let me write it. So the right-hand side on the right-hand side is, roughly speaking, Grom-Witten theory of P1, meaning that it's a localization contribution on the moduli space of stable maps to P1. So in particular, this may be viewed as some kind of correspondence between Hurwitz numbers and the Grom-Witten invariants of P1. So this is the LC formula. Let me now mention another kind of correspondence between Hurwitz numbers and Grom-Witten invariants. And this goes by the name of Grom-Witten-Hurwitz correspondence. So let me write here. And that was discovered by Openkov Panda. This is a correspondence that essentially completely solves Gromb-Witten theory of a curve with a point insertion. So when the gamma classes are point insertions. So what is the statement of this correspondence is that if we take Gromb-Witten invariance such that gamma over here are just some point classes, then it's equal to the Hurwitz number, but the input is well, there are some corrections. So I'll explain what I wrote in a second. So the argument of this Hurwitz number over here is some formal expression, finite expression in partitions. So we take the vector space spanned by the partitions of integer d or less, such that the leading term is a partition given by just k, and then you have corrections provided by partitions of a lower size. So what does it mean geometrically? Is that essentially the Gromb-Witten invariance of a curve with the point insertions is almost like Hurwitz invariance, such that the ramification is just k plus 1, plus there is some lower size corrections associated to the Hurwitz numbers. So roughly speaking, inserting psi k with a point insertion is equal to ramification of order k plus 1 plus where did they do there? Plus some corrections, such that these corrections are completely explicit. So these are the two fundamental results in this field. On one hand, this result, for example, is a powerful tool to determine the intersection theory on moduli spaces of curves. So this side can be explicitly computed in terms of the representation theory of a symmetric group, as I told you in the very beginning of the lecture. This side is much more intricate. So these integrals of lambda classes and psi classes, at least from the first side, it's not clear how to compute it, but this formula provides a way for a computation. In particular, yeah, it's an extremely important result in the intersection theory of moduli space and of very fundamental importance in the intersection theory on the moduli space of stable curves. This result, on the other hand, well, it completely determines the Gromb-Witten theory of curves, because again, this side, well, at least with the point insertions, this side is explicitly computable in terms of the symmetric group, and this formal sums of the partitions, which I actually didn't call. They are called completed cycles. Completed cycles. They're also explicit. So in particular, the Grom-Witten theory of a curve is equal to the very explicit formula on the right hand side. So let me now talk about why all of these results actually hold. And at first they might appear slightly mysterious because they relate very different types of invariants. But in fact, the key to understanding why such correspondences should hold at all is well, just in front of us in some sense, because if we consider an arbitrary stable map, so as I drew over there, so an arbitrary stable map can be always decomposed as some ramified cover with the contracted components, right? So if you give me an arbitrary stable map, you will always find the component inside it, which maps in a ramified, well, as a ramified cover to the target, and then you have some contracted components attached to it. So pictorially, it just looks like this. So we have some ramified cover. You have some contracted components. All of that is mapped to the point in the target. But this guy over here, so this guy is a ramified cover with some ramification profile, while these are contracted components. And in total, this gives us some stable map. So in particular, what it means is that, roughly speaking, the difference between stable maps and ramified covers are just these contracted components. And heuristically, we should be able to express, well, to decompose all stable maps into ramified covered contracted components, and that should give us relations of such kind. So heuristically, what I want to say is that so stable maps are equal to ramified covers times contracted components, where you sum over all possible ways to decompose summation over all possible ways to decompose stable maps into ramified covers with contracted components. With contracted components. And this can be given a completely combinatorial, well, there is a completely combinatorial gadget that allows us to encode such a decomposition. And this is just provided by a star-shaped graph where the root vertex is given by the genus of the component that maps in a ramified fashion on a target, while the leaves are given by the genera of these contracted components. Such that we also have labels on our edges, which are given by the ramification profiles of the ramified cover. Okay, so we have some ramification over here. There is some ramification profile provided by eta. Okay, and so in some sense, stable maps are equal to summation over star-shaped graphs of such kind, which then encode how we glue ramified covers with the contracted components. So how do you actually formalize this? So this is heuristics. Let me now give a more precise formulation of this idea. And in order to give a precise formulation, well, we need a way to actually write equations like this. So we can do it just in terms of numbers, but we also can do it in terms of classes. So for example, you can consider the cohomology or moduli space of stable curves and the associated cycles to the moduli space of stable maps or admissible covers. Okay, so precise formulation. So to do that, consider the projection from moduli space of stable maps to moduli space of stable curves, where you just associate a map to a map, you associate just the marked curve. And similarly, we can consider the projection like this as well for the Hurwitz spaces, so for the admissible covers. Where you just, again, forget the target and remember the source. Such that you mark the points, the branching points, so ramification points in your source. So with these maps, we can now define so-called Grove-Witten cycle. So this is just a push forward of the virtual fundamental cycle of the moduli space of stable maps. And similarly, we can define a Hurwitz cycle, which is also just a push forward of the usual standard fundamental class of the moduli space of admissible covers. And now the precise formulation of this formula over here takes, So that's the main theorem of the talk. So theorem with the Max and Johannes is that so the Gromov-Witten cycle is just equal to the summation over all graphs, or like star-shaped graphs is here, star-shaped graphs. So it's equal to the summation of over all star-shaped graphs of such kind, such that to each vertex, so to each root vertex, to the root vertex of each graph, we associate the Hurwitz cycle. And then to each leaf vertex of that graph, we associate the product of so-called I cycles, which are responsible for the contracted components. And what are those I cycles? So those I cycles, I unfortunately erased the LSV formula. So essentially they are LSV kind cycles. So it's exactly the same formula that I wrote down. Well, roughly speaking, it's the same formula that I wrote down before. So it's a sum of these lambda classes. And then we have psi classes on the bottom. And so this formula essentially formalizes these heuristics over here. So it expresses a Gromov-Witten cycle in terms of the Hurwitz cycles, and then cycles associated to contracted components. And now this takes place in the cohomology. Yeah, I forgot. So all of that lives in the cohomology of some moduli spaces of stable curves. So this is a cohomological relation of in fact highly intricate nature in moduli spaces of stable curves. Such that it just formalizes this formula over here. So any Gromov-Witten cycle is expressible as a Hurwitz cycles times these cycles associated to contract components, and we sum over all possible ways to glue them together. And in particular, now, so this takes place in the cohomology, but if we want to get, for example, Gromov-Witten Hurwitz correspondence, what we do is just we take this cohomological relation, we hit it with psi classes, and it spits out the cohomological relation, the numerical relation as a Gromov-Witten Hurwitz correspondence, but also for the LSV formula, it follows in exactly the same manner. So we take the cohomological relation, we hit it with the psi classes, and you obtain a numerical relation, which will be the LSV formula or Gromov-Witten Hurwitz correspondence. So in particular, all of that is, generalizes Gromov-Witten Hurwitz correspondence. And also LSV. And in fact, it completely solves the problem of the comparison between admissible covers and stable maps in the most general setting. So in fact, you also can take a moving curve, for example, X doesn't have to be fixed. It can vary in the families, or for those who know the subject, you can also introduce the relative points and with extra ramifications and so on and so forth. So let me now say a few words about how do we prove this. Probably over here. Yeah.
Does the proof depend on the ERSV formula, or it gives a new proof of the
It
ERSV?
gives a new proof.
Okay, cool. Thank you.
In fact, it promotes LSV formula to cohomological relation as well. So, I can tell you more about it. But let me just say a few words about where is my white chalk? Here it is. So let me say a few words about how we prove it. And the idea, in some sense, is quite simple. So we introduce for all positive real number, when introduce a moduli space that shares the properties of both admissible covers and stable maps. And we call it a moduli space of epsilon unramified maps. And such that, roughly speaking, so it parameterizes maps to X with bubbles, such that we constrain the singularities of our stable maps. So we put some leash on, for example, on how big the contracted components of stable maps can be. So first of all, one of the conditions is that, roughly speaking, contracted components are of genus less than epsilon. And then there are more technical conditions that follow. And this map, these moduli spaces, they provide, well, they generalize both moduli space of admissible covers and moduli space of stable maps. So if you, for example, take epsilon very large, you will recover back the moduli spaces of stable maps. And if we take epsilon smaller than 1, well, it says that there are no contracted components at all. And so we, in fact, recover moduli spaces of admissible covers, well, with some ramification, but let me not talk about how ramifications enter the picture. But in between, we also have this hybrid, whole family of hybrid spaces for every value of epsilon, such that they stay constant in some chambers and then change abruptly at the special values, which are called of epsilon, which are called walls. And in algebraic geometry, when you have a situation like that, it means that, well, in more technical terms, it means that we have a stability parameter, and to each stability parameter we have an associated moduli space, and then if we want to compare the associated intersection theories of those moduli spaces, we can write down wall crossing formulas. And so in particular, this main theorem is in fact just a wall crossing formula. So is equal to the wall crossing formula associated to the variation of parameter epsilon. So what it means more explicitly is that instead of comparing the intersection theory of this, so the enumerative invariance of these extremal cases, we can compare the enumerative invariance associated to these moduli spaces for epsilons that are close to each other. And this is a much more feasible task. And so for each wall, we then can compare the associated invariance, and then we collect the corresponding formulas by crossing all the walls when we go from here to there. So this what means. This is what the wall crossing formula means. So wall crossing formula. And I should say, so the idea for a proof of such wall crossing formulas came from a slightly unrelated context of enumerative geometry called quasi-map theory, and in particular Yang Zhou, who is in the audience and who also will speak on Thursday. So I very much advise to go to his talk if you're interested in topics like that. So the ideas of Yang Zhou were were extremely central or crucial for a proof of this theorem. So ideas of Yang-Zhou from quasi-map JT quasi-map. Yeah. So I guess that's all that I want to say. Thank you very much for that time.
Thank you for this nice talk. Any questions? Yes.
So in this story, so X is fixed, right? So
Yeah.
what happens if you vary the Complex structure of X?
Yeah, exactly the same formula holds. It's just you interpret this H differently. So if you can vary X and yeah, so exactly the same formula holds. It's just that this cycle becomes admissible cycle associated to moduli space of admissible covers of a moving curve.
Okay.
And this also becomes Gromb-Witten cycles associated to moduli space of stable maps of a moving curve.
All right. Okay. Thank you.
Another question? No? I have a very basic question because it looks like it's difficult to compute the Hurwitz number. And so I want to know if given a positive integer d, you have an upper bound for this number.
For which ones?
Hurwitz number, the first one that you defined. Hurwitz number, yes.
Yeah. Well, you can write them down as some trace formula of a symmetric group. So
yes. And do you know for which tuple eta 1, eta 2, eta k, this number is maximal?
Maximal in what sense?
It's the minimum lower bound.
Well, yeah, I don't know. I mean, they're quite explicit in some sense. So you can study asymptotics as well of those numbers. I mean, there is lots of work done on that. But in terms of bounding those numbers, yeah, I don't have in mind any particular bound. But I think people who are more knowledgeable in the study of representation theory of symmetric group, for example, can give a more precise answer to that question. Thank you.
Another question? If not, we can approach the speaker again.